1, and I have just gone through the queries which students have raised. So I did not find many. So first I will go through the queries which we received in our online portal, and then I will wait for the new queries which may come now during the live session. So I hope all the lectures are going well and you don't have much difficulties in these first 3 weeks. So whenever you have difficulties, it is always nice that you put your queries well in advance before the live session, because it's much easier for me as well to prepare those queries, maybe slightly in a different way that was taught during the lecture. But if there are queries during the live session as well, so I will try to answer those to certain extent based on the material which I have from the lectures. But the queries which I received before in hand, so those I can prepare much better and we can discuss during these live sessions. So let me just go through the queries which I see from the web portal. So I'll share a file here, and that's exactly which you must be able to see now. And here the first query was that someone asked that I want to know what are the current research area in engineering mathematics related to communication system branch. And it will be helpful if some information on, for instance, conferences and journals I can tell to the students. So just within the framework of this engineering mathematics, I must tell that these topics, for instance, the linear algebra and differential equations, Fourier transform, which the Fourier transform will be discussed in engineering mathematics too. So these are topics mainly. So the linear algebra, that is very important, and also the differential equations, because most of the models finally they turn up as a differential equation, and the Fourier transform, the most important in communication problems. So these are the fundamentals which are must if you want to really do some research or go ahead or go for higher study in communication system. So all these three topics are very much covered in our basic mathematics. And regarding the conferences, for instance, though I am not the person of this communication engineering or communication systems, but I know there are some popular conferences. For example, IEEE Globecom is a conference which is there every year, and there is an optical fiber communication conference. It's the largest global conference for optical communications. So these are, and there are many more. So it's a very trendy area these days. And with respect to this engineering mathematics, so definitely here this linear algebra, differential equations, and Fourier transform, these are the most important topics which one should go through if you are planning for a higher study or research in this communication system. So that was the one query which I could see there. The second query which I have taken, that was that in the sufficient condition, in one of the lectures I mentioned that the partial derivative exists and is bounded, and that was basically the sufficient condition for the continuity of partial of derivative of a function. So there the question was that how to find these bounds and how to check that the function is bounded. So definitely, I mean it's a very good question, but it's also very difficult to actually check in many cases that this function is a bounded function. So for instance, a very simple function, just for demonstration I have taken, for instance, if we have a derivative of some function, the derivative is given here 1 over x square when x is not equal to 0, and the value of this derivative is 0 whenever we have x equal to 0. So in this case, if we look at that what is happening to this function f prime around this x is equal to 0, the value of the function is 0 at x is equal to 0, but this is not bounded around this x equal to 0. So however, I mean, whenever you leave this 0 there and you go for a small value, because for the neighborhood around this 0 you have to take some neighborhood, so number of points around this x equal to 0. So since at x equal to 0, this 1 over x square will go to a very large quantity, and basically in this neighborhood we cannot bound this 1 over this x square by some, let's say, constant which does not depend on that neighborhood. So this is not possible here, because the close the x, the value of x closer to 0, you get a very, very large number with this 1 over x square, and therefore we cannot bound this function by any constant in the neighborhood of x equal to 0. So this is an unbounded function. And then there are many theorems, for instance, when we are talking about closed and bounded domain in case of such functions, function of one variable, indeed for the function of two variables as well. When we have a closed and bounded domain and our function is continuous, then we know that the function will be bounded. So these are the very basic theorem which I am referring here. But when we really want to find that a function is bounded or not, then we have to go for the advanced analysis, and there are many other results available which helps us to find upper bound or the bound of the function if it exists. But still it is a very challenging area in mathematics where we need to find the boundedness of the function. So this is a very good question, but we to answer this we need a bit more knowledge for advanced analysis, for instance. Well, so then there were two quick questions on please explain how this limit when x approaches to, so we are talking about the limit here when x approaches to infinity, and this sine x over x. So in this case, it's trivial. Basically, we don't have to do much, because we know that the limit here when x approaches to infinity, which is a trivial limit, is very standard result when we have 1 over x and x goes to infinity. So in that case, this limit goes to 0. We all know that. And here we have sine x over x. So the sine x, another result which is also well known, that the sine x function is a bounded function, and the value lies between -1 and 1 in the closed interval -1 and 1. Whatever value of x we take, sine x always, the value of sine x always lies between -1 and 1. So this numerator here, this is a bounded function. So this is bounded. This is a bounded function, and when something is bounded there and 1 over x is going to 0, so 0 into something bounded will be 0. So this limit is just 0. So it's a simple argument where the boundedness of this sine x plays an important role, and the result we have here, this 1 over x goes to 0 as x approaches to infinity. So that's one part. So here, and the second one, we someone asked about the curve tracing. So this is again a very wide area where we can have many lectures on curve tracing, and mainly then we have to go through the convexity, concavity, asymptotes, And then of course the applications of derivative will play a role, where we can find out where the function is increasing, where it is decreasing. So many uh, information we need about the function to really trace it. So this we eventually we did not cover in this engineering mathematics uh, course. But if we add, for instance, the information on convexity, concavity, asymptotes, etc., then we can have, and of course we have already the idea about the relation of the derivative to the behavior, increasing, decreasing of the function. So with all these information, we can get some idea that how this curve will look like. So that's the topic you are talking about in curve tracing. I did not see any other comment, and let me just take a look here if anything new is there. Okay, so some students are in the last time also I remember, so they ask about the engineering entrance exams like GATE, whether the syllabus is covered in this. So just let me tell you, these engineering mathematics 1 and engineering mathematics 2, so they are very basic fundamental courses which we usually do in BTech first semester and second semester. So obviously we go time to time to a very depth whenever there is a topic which is also there in GATE syllabus, but still for the GATE, because that is for the master's students, and you have to do a bit more for the GATE. So this just doing this course may not be sufficient, because it does not cover all the topics also, which may be in the syllabus of a particular stream for GATE. But yes, definitely whatever we have covered here, it is also to certain depth. So definitely you have to go through first these engineering mathematics 1 and mathematics 2, and then we can uh, go for the extra hours to learn more on the syllabus of GATE. So we will wait for your comments. Meanwhile, what I can do, so I can uh, just go through the some review kind of things, which I can now share with you. So just wait. Well, so meanwhile I receive your queries, I will just summarize some important concepts which we have covered in this course. Well, so here we have some review, and I have taken some really complicated stuff from this differential calculus, which is already there in these first 3 weeks. So there might be some confusions, etc. So maybe I will clear them again. So first of all, the concept of limits, which is very different when we talk, or when we comes to the 2 variable case or 3 variable case. So in case of one variable, we usually talk about two paths. So when we want to see that there is a function and we want to check what is the limit when x, so this is the x-axis, and we can call the other one y-axis. So here we have x and y-axis. So when we talk about the single variable case, so we have two possibilities only. We can approach from the right hand side, we can also approach from the left hand side. So there were two paths, and we usually take the limit as x approaches from the right hand side, also when x approaches from the left hand side to this x naught. And if these two limits are equal, then we say that the limits are, then the limit of this function at x equal to 0 exists, otherwise it does not exist. So the concept was very clear, and there was no confusion when we are talking about the function of one variable. But as soon as we go to the function of second variable, then the concept of this path is very different. Suppose we want to go to this point here and we want to check the limit of this function. So here we can say like it's x0 and y0 point, and we want to take a limit, that what is the limit of this function as this x goes to 0, y goes to 0. Then there are several paths. So you can approach to this point within the domain from infinitely many directions, and that is the point of difficulty when we talk about limit for the functions of two variables. So this is the new concept in as compare as we compare to the one variable case. So the difficulty here is that there are infinitely many paths, so we cannot keep on checking those infinite. That's not possible. Keep on checking those paths and see whether the limit is different or it's the same. If we can find any two paths where the limit is different, then we are done and we can conclude that the limit does not exist. But if we take several paths and the limit is same, we cannot conclude anything, because there might be some path which we may not see trivially where the limit is different, what we are getting along several paths. And that is the difficulty we have when we talk about the functions of two variable. So in this case, the limit cannot be obtained by approaching the point along a particular path. So that is very clear, because there are infinitely many paths and we cannot fix the path where we can find the limit and we can conclude that this is the limit in case all those paths are having same limit. So it's a very clear concept that and it is very different than the single variable case where we have only two limits and we can conclude that limit exists. So in this case, there are other ways which we will discuss or we have discussed already in the lecture. So one thing is very clear: if the limit is dependent on a path, then the limit does not exist. That is clear. If we have two paths, we have shown that there are two paths here where the limit is different, then we can conclude easily that limit does not exist. But if you want to know that what is the limit in case limit exists, then what shall we do? So that we will discuss briefly in a minute here too. So just to illustrate the idea, these two examples, which are everything is discussed in the lectures. So it's just a repetition, maybe a different style of explaining, nothing else. So if we talk about these two examples, x square y and x4 plus y square, and we take the path y is equal to x. So our domain is the xy plane here, and we want to approach to the 0, 0. So one path we have taken that along y is equal to x. Y is equal to x, we want to approach to this point 0, 0. So how to approach that? So y is equal to x, that means y and x are equal, so that we can set in this function that x and y are equal. And when you put this x and y equal, so you have here x cube, and here you will have x4 and then again x square. You take common and then let x tends to 0, and you will see that you can show that this is actually 0. And but when you take y is equal to x square, then what will happen? The limit you will get, that is 1 over 1 by 2. And in that case, when you have this limit 1 by 2, because when you put y is equal to x square here, what will happen? You have x power 4 there in the numerator, because now you are choosing a different path. So you are approaching to 0, 0 along this y is equal to x square. So that means y is x square. So we can reduce this two variable problem to 1. So we have y is equal to x square, we got x4 there, and we have again x4 in the denominator, and then we have y square, which is again x4. So what happened here? This is nothing but 1 by 2, and limit x goes to 0. So we have basically 1 by 2 as the limit. So the example was very trivial, and here we could easily see that in one way the value is 0, and in another way or another path where y is x square, the limit is 1 by 2. So the two different limits along two different paths, and we can easily conclude that the limit does not exist. So it's fine. So it's very conclusive whenever you can find two paths where the limit, but suppose along these two paths, the limit is same. Here we got 0, and suppose here also we got 0 in the second case. In that case, we cannot conclude anything. We cannot say that the limit is 0. Special path where the value might be different. So definitely just fixing some path, we should not conclude the limit. That is the remark here. If we take xy and then x square plus y square, for instance, we take y is equal to mx. So mx means we can take any line, m can be anything. So we are approaching to the origin along a different lines. So in that case, what we observe here, that the limit when you put y is equal to mx, there you are getting m over 1 plus m square. Again, it's very clear here that for different value of m, so if you have the different slope approaching towards the 0, 0, then you are getting different value of this limit. And again, the limit depends on path, and we can conclude that this limit does not exist. The alternative approach, which is actually very useful, is to change the coordinate system. So from Cartesian to polar. And remember, a very important point here, which I want to make it clear, that here we are changing the coordinate system. That means from Cartesian, where we talk about x and y, and now we are talking about r and theta. So these two are different Cartesian system. We can have any curve in xy, we can represent that curve also in the polar coordinate. So there is no restriction. Whatever you can represent in Cartesian coordinate, the corresponding curve, the same curve you can also represent in polar coordinate. So these are two different coordinate system. And here the relation we have, x is equal to r cos theta, y is equal to r sin theta. So we can change our function xy divided by x square plus y square into the polar coordinates. And when you do that, so x is r cos theta, y is r sin theta. So r square will be there, sin theta cos theta, and here x square plus y square will become r square. So r square term from the numerator, from the denominator, it will cancel out. And then we have cos theta sin theta. So, and then theta, for any value of theta, r actually goes to 0. So here xy goes to 0 means r tends to 0 irrespective of theta. So here there is no r, so we got cos theta sin theta as a limit. That means for different value of theta, we are getting different value. And r, you can let r to 0. So there is no r, so there will be no difference to the limit. So the limit is cos theta sin theta. And this is not the limit of the function because it depends on theta. So for different value of theta, we have different limit. So that means the limit, this xy goes to 0, 0 xy or x square plus y square does not exist. So this changing to Cartesian coordinate is very helpful in either case, to get the limit or to prove that limit does not exist. So this was an example where we have shown that limit does not exist because it depends on theta. And so for different value of theta, we are getting different value. And we will see some examples where changing the polar coordinate, we actually get a conclusive limit. So the limit does not depend on theta. That means whatever theta is and r approaches to 0, so we are getting 0. So in that approach, we are covering actually all paths. So we are covering all infinitely many paths. We are not fixing any path. We are just changing the coordinate system. And if we are able to show that the limit of the given function is something which does not depend on theta, and of course does not depend on r because r will go to 0, so in that case we can conclude easily that this is the limit. So we will see some example probably in this review slides itself. So for instance, here we want to change to the coordinate system from Cartesian to polar. So we will apply this transformation r cos theta and r sin theta. When we do so, because if you see here, x square y and x square plus y square. So when we have these coordinate systems, the new coordinate system, r cos theta, we will put here r square, so cos square theta. So what we will get, just let me just write down here. So we will get r square, we will get cos square theta, y is r sin theta, so we will get r sin theta, and then here we will get x square plus y square is equal to r square. So this r square and r square will be cancelled, and we are talking about r tends to 0. So when r tends to 0, this everything will be 0. So because cos square theta and sin square theta, so these term will be just some bounded terms. So sine square theta as well as this cos square theta, they both are bounded functions. So we will get here equal to 0. And so it's clearly in this case, the limit is 0. The limit here is 0 because the limit is not depending on theta. So irrespective of theta, so it's independent of theta, we got the limit 0. So there is no confusion here that we have fixed some path. This relation x is equal to r cos theta and y is equal to r sin theta, we are not fixing any path. We are simply changing the coordinate system. So in the new coordinate system, we can have any path. We can represent a curve by this new coordinate system by in terms of r and theta. So what we have realized that after changing it, we got immediately our limit as 0. That means this limit does not depend on the path. It does not depend on theta. It does not depend on path. So this is the limit. So therefore, what I said, that this changing the coordinate system is very useful, and we actually we can get the limit here by doing this. So here my YouTube link is not working. Let me just see. Okay, so first let me go through this. So here we have this limit and no dependency on theta. Hence, this limit does not exist in this case. So we go next to, just give me a minute here. I will connect to the system, YouTube system, so that I can receive your queries. And just give me a minute. Okay, well. Yes, so we have seen this, that there is no dependency on theta, and therefore we can conclude in this case that the limit is 0. So what is again very important, which I want to mention here, that changing to polar coordinate does not always help. In fact, this transformation may sometimes tempt us to give false conclusion. And how this false conclusion? For instance, we see this example, x square y over x4 plus y square. And we change the coordinate system to the polar coordinate. And what you realize now that we have r3 there, we have r4, we have r square. So what, after this cancellation of r square, we have r cos square theta and sine theta, and in the denominator we have r square cos 4 theta and sine square theta. When we let this r to 0 now, to go to the origin, to go to x equal to 0, y equal to 0, what will happen? We may conclude that, okay, this r is 0, so we have numerator 0, and denominator we have r square, so this is also 0, and sine square is something which we may ignore here, and then we will conclude that this limit is 0. So basically, if we fix theta, that conclusion is fine, that this limit will be 0, but that means we have fixed some theta, then only you can get this limit 0. So we can conclude that if we fix theta, we can get it 0. But again, that we are here putting a condition that this is 0, that theta is fixed. But we cannot fix theta. If we are fixing theta, that means we are fixing path. So this limit, if comes without fixing any theta, then only we will say that this is independent of path. But in this case, it is not independent of path, because this limit, you are getting 0 when you fix some theta there. Otherwise, the problem is that you may get like 0 by 0, which is not 0, because you have 0 there, you have 0 here, but this sine square theta can also be 0. So getting this limit only for fixed values of theta, and what we can see here easily, that if we take y is equal to x square path, meaning this sine r sine theta is equal to r cos square theta, this particular path, and we can easily show that actually limit is half. So this, we have to be very careful when we pass this limit r tends to 0, and so that we can basically don't overlook that we have fixed actually theta, then only we got that limit. Well, so, and then we talked about the continuity. So the limit and the continuity, eventually, once we understood limit, so the continuity is clear, because here also we talk about mainly this third part, that the limit of fxy as xy goes to that point is equal to the function value. So these two obvious, so the function should be defined at that x0, y0, and then this limit should exist, and the limit should be equal to fx0, y0, then we say that the function is continuous at that point. So this concept is exactly analogous to what we have for one variable. Well, so for discussing the continuity, we eventually have to compute the limit. So for instance, in this case, so we take the x is equal to and r cos theta, y is equal to r sine theta, and now we are in this condition, so r and this one, and again the same problem, we should not ignore this, that we assume that, okay, this is something here and r tends to 0, so we can basically get this limit 0, but that's wrong, because something unbounded sitting here, and we cannot just simply let r to 0 and the whole limit is 0, so that is wrong. And so again, if we fix theta here, then the limit is 0, that there's no problem. We fix the theta here so that it is something bounded, and then r to 0, you will get some limits here 0, but again, these are path dependent, so finally the limit does not exist. In this case itself, if you take, for example, y is equal to mx, so it's 0. So any path, any line you take, the limit will be 0. But there is another, as I told, there can be very different path. So here, if you take y is equal to minus x e power x, so this is also going to 0, right? When x approaches to 0, y is approaching to 0. So you are approaching to origin along this path as well. But when you do this substitution there, you will realize that the limit here is minus 1 by 3. Yeah, so the limit is minus 1 by 3. So the limit does not exist. Hence, the function is not continuous at 0, 0. And very interesting part, maybe another 5 minutes I will go through, and then maybe I will look into your queries there. So the usual derivative of a function of several variables with respect to one of the independent variables, keeping all other independent variables as constant. So the concept of partial derivative is very much the same as the concept of the derivative of a single function. And in this case, what we do, so for instance, we are talking about a function of two variable x and y. So we can treat one as constant. So if we are talking about partial derivative with respect to y, you keep x, or you treat x as constant and do the usual derivative which we know from the function of one variable. Or fundamental definition, we can have like partial derivative with respect to x at x0, y0. And this is the fundamental definition, and very useful definition, so we should keep in mind. So here the variation with respect to x, because we are talking about x, y is like constant, so we have fixed here y naught in both the cases. We have done the variation in this x naught, so in this first case, so and divide by this. So that's the definition we have in single variable, and here also we are applying that definition. So this is what we have, or in other way around, you can understand this, that just fixing this y, you just have a function of x, you get the derivative, and then finally you substitute x is equal to x naught. So I can see immediately one query here which is related to what we are talking about here, that r tends to 0, then what about theta? So because the problem, they are going both xy tends to 0. So, okay, why we are putting only limit r tends to 0, then what about theta? Yeah, so okay, so just see, so we have the polar coordinate. What we do in polar coordinate, we represent a point by two things. So one is theta and one is the distance r, right? So for example, the coordinate of this point, we have r and theta. So what is r? R is the distance from this origin, and theta is this angle which we are approaching from here to here. So this y, we want to go to this point, for instance to 0, 0. We want to go to 0, 0 from any points in the neighborhood. So if we let just r to 0, and that's actually the convenience we are looking at, that by changing the polar coordinate, we are able to get the limits. We are able to decide whether this limit does not exist or this limit exists. So exactly, that is the point. It's a very good question somehow for the clarification. So when we are letting this r to 0, forget about theta. So what will happen when r tending to 0? Forget about theta, whatever theta you imagine, you imagine, but what will happen when r tends to 0? Basically, r tends to 0 means you are approaching towards this 0, 0 point, irrespective of theta. Theta might be from this angle you are approaching, this angle, this curve you are approaching, this curve, and so on. Any curve you imagine there, and you want to go to this origin 0, 0, so that letting this r to 0, that is enough. Letting this r to 0 is enough, because irrespective of theta, if you let r to 0, you are basically going to the origin. So that's the reason that xy tends to 0, 0, the equivalent condition in polar coordinate would be just r tends to 0, because if you fix theta, that means you are fixing the path. So suppose you have fixed theta, you have you from this point you want to go to this origin. So let me just see. So here we have a point, here we want to go to this by changing our theta, by varying our theta, then we can follow any path. So here my theta was something else, here my theta is something else, and so on, and then I'm r2 0, but finally you keep on varying your theta, does not matter. Only if you keep constant your theta and approach to the origin, you will follow actually the straight line. But if you keep on varying, then you will follow some path. If you keep on varying randomly your theta, you will follow some path, but at the same time you are letting your r to 0. So finally you are going towards the origin, because this r is the distance from the origin. So if you let this r to 0, that means you are approaching to 0, 0. So I think it's clear now that why we take just r to 0. So what is the next question? Okay, Taylor's theorem, Cauchy from remainder. Okay, I'll keep in mind. So maybe the next time I will explain this. There is a query. So again, I'm repeating here that whenever you have query, we give enough time to raise those queries. You please raise your query well in advance based on those lectures, and then I will prepare before this live session so that I can discuss more precisely and slightly in a different way than discuss in the lecture. Okay, so let me just go through some queries, otherwise I will continue a bit more there. So, okay, material, this is okay. Okay. So someone is asking physical significance of curl in vector calculus. So what you can do, maybe I can tell you, there are lectures on engineering mathematics too. Probably they are available on YouTube as well. So you go through those lectures in my this YouTube, and then you will see that this physical significance of this curl is well explained in this vector calculus portion. Yeah, so you please do that. And sir, are these things taught in IIT KGP first year? Yes. So basically these maths 1 and maths 2 in this NPTEL lectures, I have included in fact two courses which we teach here in IIT Kharagpur. So one is mathematics 1, mathematics 2, and there is another one, transform calculus. So these three courses in IIT Kharagpur are covered in these two courses of NPTEL. So mathematics 1, engineering mathematics 1 and engineering mathematics 2. So here there is an extra course also included, which is transform calculus, where we talk about Fourier series, Laplace transform, etc., which is also covered in engineering mathematics 2. So you can go through the engineering mathematics 2. So here we have the meaning of the convergence you have asked here. So that is also, I will refer to the lectures on engineering mathematics 2 where we have discussed this, or if you want to learn now, you just go through that and we can you can get back to me for your queries. So here this is done, and the Taylor's theorem, Cauchy theorem. So the Taylor's theorem and Cauchy theorem, maybe I will go through in the next session, because you can go through again to the lectures, but we have already so I have to prepare slightly differently so that you can get really more into it if you have this query there. So we have another 5 minutes, let's say. So I will continue this. So we have the partial derivative. The concept of partial derivative is nothing but it's the same thing as we talk about in one variable. So that is not at all different. Just fixing one variable, or when we have three function of three variable, you can fix two and compute with respect to one variable. So that is absolutely fine. What is interesting here is the partial derivative and continuity. In fact, more interesting stuff I will be talking about now when we go through the example. So the point here is that a function can have partial derivative with respect to both x and y at a point without being continuous there. So that is interesting here, which is this concept was different when we talk about simple derivative in one variable and continuity. So there the continuity is must for the derivative. That means that is the necessary condition that the function must be continuous to have this a derivative there. So in this case, when we have this concept of partial derivative, it is not the case. Without being continuous, we can talk about or the partial derivatives exist, or the other way around, that the partial derivatives exist and the function may not be continuous. So that is a very different topic as compared to the one variable where you are familiar with. So here I will show in this first example that this function is continuous at 0 0, but its partial derivative do not exist basically. That means again, so here the function is continuous and its partial derivative does not exist. So that is maybe similar to what we have in one variable calculus as well. So here the continuity I will skip, which is again very trivial because we have the sine function, which we always say, I mean, which we have we'll take some fixed value and then x plus y. So when xy goes to 0 0, the whole thing will go to 0. The function value is also 0 there. So at 0 0, this function is continuous, so there is no issue. And when we talk about the partial derivative, so this is our function. So what is again the confusion some of you might have, that calculation of this partial derivatives, now if your function is given in such a form that it is defined separately at that point at 0 0 and different at the other points, you should always apply the fundamental definition of the derivative. You should not just get the derivative of this, because that would be the derivative where x plus y is not equal to 0, but we are talking about the derivative at 0 0 point where x plus y is equal to 0. So to do that, the only way is that you always talk about the fundamental definition. So in the fundamental definition, we have f delta x 0, and we have minus f 0 0 over delta x, and the limit delta x tends to 0. So this is just the fundamental limit we are talking about. So x not 0, y not 0, because we are talking about the partial derivative at 0 0. This is what I kept here. So we have f delta x comma 0 minus f 0 0 over delta x, and then you use this definition, and what you will realize here that this delta x and delta x gets cancelled, and we don't have this limit, because sine 1 over delta x as delta x goes to 0, we know that this is something finite, something bounded, but we don't know what exactly it is. So this limit does not exist. That means the partial derivative does not exist. The function was continuous. The partial derivative does not exist with respect to x. Similarly, with respect to y as well. And we have a function here which is continuous, and its partial derivative exists. Is not continuous. Sorry, this is the other way around. So here the function is not continuous, but its partial derivative exists, and that is actually different what we usually see in case of the calculus of one variable functions. So here if we choose like 1 y is equal to mx, and immediately we will see that the limit depends on the path, so meaning that the function is not continuous, because the function value is 0 at x equal to 0, y equal to 0. And when we are letting this from the neighborhood towards the 0 0, we see that the limit depends on m. So this is not a continuous function. So the limit does not exist, and hence this function is not continuous at 0, 0. And when we calculate the partial derivative, again, here you have to use the fundamental definition. Don't just get the partial derivative of this xy over x square plus 2y square, because that will be the partial derivative where xy is not equal to 0. We want to get partial derivative at 0, 0. For that, you need to write this fundamental definition. So that's a mistake, or most of the time students do or they do not understand here. So we are talking about the partial derivative at this point 0, 0. So don't just differentiate this by keeping one constant. So here we have to apply the fundamental definition. So with respect to x, we have here and 0 minus 0 delta x. So you will get the value 0. So this is the partial derivative with respect to x. And similarly, the partial derivative with respect to y, we can get again, that is 0. So we have seen in this example that the partial derivatives exist, whereas the function is not continuous. Well, this is another important result which I will just read here. So the function has partial derivative everywhere in a region, and it's bounded. So the boundedness again, which I already explained at the very beginning. So we have the boundedness of the partial derivatives, which is very difficult sometimes to prove that this function is bounded. And in that case, if these conditions, so the partial derivative exists, because we have seen the existence of partial derivative does not imply the continuity of the function. So here the existence of partial derivative and some boundedness here, that will imply the continuity. Or there is another sufficient condition. Remember, there could be several sufficient conditions. So you can put more and more restrictions, and still you can make several sufficient conditions. So here we have that one of the first order partial derivative exists and is bounded in the neighborhood, and the other exists. So we have a better condition here, that we are not talking about boundedness of both. Basically, boundedness of one is enough, and the existence of both. So if you want to prove this continuity, this could be another way of doing that. So but nobody will do this, because directly continuity perhaps will be easier. Now we come to the differentiability, and that is actually very involved. You must have several queries on this, and definitely maybe in the next live session, I will be very happy to clarify those queries, because when we talk about the differentiability of the function, it's much more complicated. So I think the time is also running, and I don't see many queries here. So what is the limit of the greatest integer function is equal to 0? And so there are a few more queries, but I'm supposed to stop here now, 5:25. The next slot will start. And whatever queries left, so I will keep it for the next live session. And please update, I mean, you well in advance, you put your queries so that we can discuss during this live session. I can prepare well in advance, and then we can have a better explanation during these live session. So I thank all of you for attending this, and then I will wait for your queries for the next live session. So thank you very much for your attention.
Sir, please wait 30 seconds, sir.